The small angle approximation is a useful simplification of the basic trigonometric functions, which is approximately true in the limit where the angle approaches zero. They are truncations of the Taylor series for the basic trigonometric functions to a second-order approximation. This truncation gives, where theta is the angle in radians. The small angle approximation is useful in many areas of physics, including mechanics, electromagnetics, optics, cartography, astronomy, and so on. Justifications. Graphic. The accuracy of the approximations can be seen below in Figure 1 and Figure 2. As the angle approaches zero, it is clear that the gap between the approximation and the original function quickly vanishes. Figure 1. A comparison of the basic odd trigonometric functions to theta. It is seen that as the angle approaches zero, the approximations become better. Figure 2. A comparison of cos to 1 theta 2 halves. It is seen that as the angle approaches zero, the approximation becomes better. Geometric. The red section on the right, D, is the difference between the lengths of the hypotenuse, H, and the adjacent side. As is shown, H and A are almost the same length, meaning cos theta is close to 1 and helps trim the red away. The opposite leg, O, is approximately equal to the length of the blue arc. Gathering facts from geometry. S equals A asterisk theta. From trigonometry, sin theta equals O, H, and tan theta equals O, A, and from the picture, and leads to simplifying leaves. Algebraic. The Maclaurin expansion of the relevant trigonometric function is where theta is the angle in radians. In clearer terms, it is readily seen that the second most significant term falls off as the cube of the first term. Thus, even for a not-so-small argument such as 0.01, the value of the second most significant term is on the order of 0.000001, or 1/10,000th the first term. One can thus safely approximate, by extension, since the cosine of a small angle is very, very nearly 1, and the tangent is given by the sine divided by the cosine. Error of the approximations. Figure 3 shows the relative errors of the small angle approximations. The angles at which the relative error exceeds 1% are as follows. Tan theta at about 0.176 radians. Sin theta at about 0.244 radians. Cos theta 1 theta 2 halves at about 0.664 radians. Specific uses. Astronomy. In astronomy, the angle subtended by the image of a distant object is often only a few arcseconds, so it is well suited to the small angle approximation. The linear size is related to the angular size and the distance from the observer by the simple formula D equals XD, 206,265, where X is measured in arcseconds. The number 206,265 is approximately equal to the number of arcseconds in a circle, divided by 2 pi. The exact formula is D equals D tan, and the above approximation follows when tan is replaced by X. Motion of a pendulum. The second-order cosine approximation is especially useful in calculating the potential energy of a pendulum, which can then be applied with a Lagrangian to find the indirect equation of motion. When calculating the period of a simple pendulum, the small angle approximation for sine is used to allow the resulting differential equation to be solved easily by comparison with the differential equation describing simple harmonic motion. Structural mechanics. The small angle approximation also appears in structural mechanics, especially in stability and bifurcation analyses. This leads to significant simplifications, though at a cost in accuracy and insight into the true behavior. Piloting. The 1 in 60 rule used in air navigation has its basis in the small angle approximation, plus the fact that 1 radian is approximately 60 degrees.